Hey all. So today, let's go with a light title. So today I'm going to be talking about, where am I? Today I'm going to be talking about the sampling distribution of sample proportions, which are a little bit different than sample means, but have a lot of similar characteristics. So let's look at our notes here. The sample proportion is going to be a point estimate of the population proportion. So the type of question we might be asking if we're looking for a proportion would be maybe something like, what percentage of voters will vote for Donald Trump in the 2020 election? So, of course, this is the type of stuff news reports on all the time, right? So the news shows us polls. And when they say something like 45% of people say they will vote for Donald Trump in the 2020 election, well, that's an estimate of the population proportion. Because what they are not doing, as you probably know, because they don't call you every single time. So how do they know if you're going to vote for Donald Trump or Joe Biden or someone else in the 2020 election? Well, they don't. But what they do is they use a sample. They pick a random sample of people, and then they calculate a sample proportion. And that's their point estimate of what they really want to know, which is the population proportion, right? What they really care about and what they're really trying to guess is the true percentage of people that plan on voting for Donald Trump. But they're not going to call everybody, so they're going to use statistics to guess. So the way to calculate that is, say they call, so poll company, so a polling company, which specializes in doing polls like this, like Gallup is example of a poll company, calls about 1,000 people. So they don't call everybody. They call 1,000 randomly chosen people that live in the US. And they might ask them some screening questions like, can you vote in the US? Because maybe some people can't vote. Are you old enough to vote, for example? And so say out of those 1,000 people they call, they find that 436 people say they will vote for DT, Donald Trump. Then P hat, the point estimate of the population proportion, which we call the sample proportion, equals 436 divided by 1,000, which equals 0.436. So more generally, P hat equals X divided by N. N, as we saw last time, is the sample size, right? X is going to be number that meet condition. So in this case, the condition is, say they are going to vote for Donald Trump, but it could be a wide variety of things. I could be asking, what percentage of blue whales are males? And I could go take my boat out into the ocean and try to find a bunch of blue whales and say I find 10 and 3 of them are males. Then my guess is that 0.3 or 30% of whales are males. Because notice, you can always turn this into a percent. You've probably done that before. You've probably calculated a lot of proportions. What is the proportion of points that I got on this test correct? Count how many you got correct, divide how many there are, and that gives you a proportion, right? So that's how we get our point estimate of our population proportion, which we call a sample proportion. We take a sample, we count how many things meet the condition. In this example, it was 436, and we called 1,000 people. So we divide it by the number of people, and we get our sample proportion. We use samples for proportions for the same reason that we use samples for X bars. It'd be really costly to count everybody in the population. Now, the expected value of a sample proportion. So if I did this over and over and over again, on average, what would I get? Well, luckily for us, the expected value of sample proportions, which are a random variable, is the population proportion. So for the population proportion, we just use P. For the sample proportion, we use P bar. So that's a good thing, because that means on average, when I take random samples and calculate sample proportions, which, just as a reminder, sample proportions are going to be a random variable. Because going back to this Donald Trump example, if I called a different random sample of 1,000 potential voters, I would probably not get exactly 436 again, right? I'd probably get something different. And if I did it again, I'd get something different again. So that means that sample proportions vary randomly. They vary randomly from sample to sample, just like sample averages do. One nice thing about sample proportions, just like sample averages, is that this is a random variable, so I might be caring about what its distribution looks like, just like when we did the dice before. Luckily for us, guess what type of distribution sample proportions come from? They come from bell curves. And this is going to be very useful for us because soon we're going to start calculating probabilities, actually in the next video. And bell curves allow us to do that. You probably did a little bit of that in the last semester, especially if you already did this chapter. And what we've learned here is that the expected value is the truth. Population proportion. So when we take a random sample and we do a sample proportion, we expect to get the truth. But these things vary randomly around the truth. And what we get is not probably going to be exactly the truth, but if we do it enough times and over again, we're going to get closer and closer to the truth. So that's the center of the distribution, the expected value. And that's how we can draw that graphically right there. But as we've mentioned before, and I've already drawn right here, oftentimes we also care about how spread out a distribution is. So we need to figure out how to calculate the standard deviation of sample proportions. We also call the standard deviation of sample proportions the standard error. So basically any time when we're calculating a statistic, whether it be a sample proportion, p hat, or x bar, so x bar and p hat, p bar, are both examples of sample statistics. Other examples of sample statistics are the median. The sample standard deviation itself is also a statistic. And really, any time we're taking a sample and calculating a statistic from it, whether it be a sample average or a sample proportion or a median or a maximum, those are all different things we can calculate from a sample. Anytime we're talking about the standard deviation of a sample statistic, statisticians call those standard errors. And we just use a different word because we want to distinguish between these and the underlying standard deviation. Now, the formula for the standard error of a proportion, a sample proportion, is a little bit different than it was for a sample average or a sample mean. So here we'll call it sigma p bar. That's going to stand for the standard error of a sample proportion. And the formula for this guy is going to be sigma p bar equals the square root of P1 minus P over N. So in this case, P is the population proportion. Sometimes we don't know that. In some of your examples, they'll tell you what the population one is, and sometimes we won't. So no, for example, what if we knew actually that the true average was 45%, but then this is our estimate in this one particular sample? Then we would use 0.45 here because that's the population proportion. But oftentimes we don't know that, and we have to guess what it is. Well, what's our best guess? It's our point estimate. So when we don't know the population proportion, which we usually don't, and that's the point, we're trying to guess it, then we use our actual P bar inside this formula. So that's how we'll calculate it in two different ways. Sometimes in the book in your homework, they'll give you the population one and you'll use this. If P known. But if they don't and you have to guess it, this is if P guessed by P bar. Now this one's going to be our infinite sample, because remember last time in the last video, infinite population. And it doesn't have to actually be an infinite population, it just has to be really big relative to the sample size. So for example, there's 300 million about voters in the US. That's going to be a big enough population where we're going to use this infinite population version. And almost every example is like that. But there's some cases where if you have a small population, so maybe the blue whale case, maybe there's just not that many blue whales in the world, then I might have a finite population. And in that case, we have to use this special adjustment. That is the same adjustment actually as the one we made when we did sample averages. That's going to be the population size minus the sample size divided by the population size minus 1. And then that will be multiplied by the exact same formula. Notice that we get the same action with n here. This standard error is being divided by n in the square root again. So when our sample size goes up, if we have a small sample size, we might have a big fat distribution, very spread out, versus if we had, so this would be like a small n, a small sample size. But if we take a really big sample, we're going to get a tighter distribution. They're still both bell curves, but sample size, higher sample size helps us. Oops, I'll do that in blue. So having a bigger sample size helps us by making this thing more tightly compact around the truth right here, which is what we want to know. So a lot of the same characteristics as we had with X bar. Now I'm going to show you on the internet some places that these are actually calculated, and we can look at how these things work in Excel real quick. All right, so I'll see you in a minute on Excel. Hey guys, so I just wanted to show you some sample proportions in the real world that are pretty similar to what we looked at in the notes video. So I'm just going to go ahead and do real clear politics latest polls. And this website aggregates a bunch of polls that happen all the time. And so these are all examples of sample proportions. For example, this one right here, President Trump job approval. The polling company is Monmouth. Approval 44. So that's 44%. So that is a sample proportion, because I can assure you they didn't call every single U.S. citizen or U.S. resident to ask them how they felt about Donald Trump's job approval rating. And so their sample estimate, their sample proportion, which is a point estimate of the population proportion, is 0.44 or 44%. Now let's check out one of these other ones, because I think some of these polling companies have pretty good backup data. This Economist YouGov one, I think, allows us to actually look into. So here's a bunch of different polls they have. And so you can look at all these if you want to. But if we click on direction of the country, so basically this gives us an idea of the data, the raw data that they did to do their sample proportion. So right here, they called a bunch of people. Notice that they have breakdowns by gender, education, income, and stuff like that. But so this is a direction of country poll. So they try to just ask people like, how do you feel about the direction of the country? And people can say either it's headed in the right direction or off on the wrong track, or they can say they're not sure. And then if you add all those three things up, you got to get 100%, right? So that's one thing that's always true of proportions, is each individual answer, if they're mutually exclusive, meaning you can't answer more than one of these things, wouldn't make sense, you get 100%. They also give us the sample size right here is 1,500. So they use capital N, but we use lowercase n as sample size. So notice we could use this information, get our handy calculator here, that is Excel. And so looking at this poll, if we wanted to, we could say, well, let's do this direction of the country, so this 30% right here. So then we'd write our sample proportion is 0.3. Make that a little bit bigger so we can see it. So that's our sample proportion. And then with that, all we need notice is that I'll put n here, that's 1,500. And now we could get the standard error based on those formulas we just went over. So the standard error is going to be equals, the square root function in Excel is SQRT. I'm going to open parentheses twice. That's going to be 0.3, so I can just click on that cell, times 1 minus 0.3. Notice I'm using P bar here because I don't know the population proportion. And then that gets divided by, come on, n, which is right here. I'm going to click on A4 and click over because sometimes Excel is dumb and it won't let me click on that cell behind here. But that's where I put that 1,500, right? Close parentheses, and that's the standard error of the proportion. So my estimate is that 30% of voters think that the country is generally headed in the right direction, because we can think about proportions as percentages. So 0.3 is the proportion, or you can always change it to a percentage by moving over the decimal 2 places, like you've probably done for grades in the past. And then this is the standard deviation of the sample proportion, or the standard error of the sample proportion. And so that's how we do that formula. So that's something that could be helpful for you in the homework, because you'll definitely be calculating some standard errors of proportions. we did not use the finite population factor here because the total population in this case is going to be more than 300 million people, probably, because we're talking either about US residents or citizens. So we don't need to use that finite proportion or finite population correction in this case, but you might sometimes, and the book gives you a rule of thumb for using that, which is if the sample is less than 5% of the total population, then you can go ahead and use this formula that I used. But if the sample is more than 5% of the population, they encourage you to use that finite correction in your calculation. All right, so I just wanted to show you a quick example of, look, here's a ton of proportion data we could get. You could do that, what we just did, for any of these proportions because they're giving the n's for all of those. And that's how we use proportions in the real world and think about how spread out that distribution is. All right, so we'll talk to you guys next.